Now, rotational motion. See, the first topic in this chapter is center of mass, the concept of center of mass. See, center of mass is defined for a system. If there is only one particle, we cannot call it as a system. See, the assembly of more than one particle. Okay, it is called a system. So, the simplest form of the system is a two-particle system. So, we will derive some formulae or equations for a two-particle system. What is true for a two-particle system can be applied for any system with any number of particles. Okay, now let us consider a simple system that is with the two particles of masses m1 and m2 and with the position vectors say r1 and r2. Then the position vector of the center of mass is given by this beautiful formula. R equal to capital R represents the position vector of the center of mass. Okay, so this is m1 r1 plus m2 r2, where r1 and r2 are the position vectors of the two particles with the masses m1 and m2. Okay, and this is the formula for the x coordinate of the center of mass. Okay, both the formulae are in the same format, so you cannot forget this. Okay, similarly you can write the formula for the y coordinate of the center of mass, or if you need z coordinate also if the system is in three-dimensional space. Okay, all in the same format. Okay, now see, let us consider an example with this one. See, this is a previous question. Okay, we have two particles of masses 5 kg and 10 kg attached to the two ends of a rigid but massless rod of length 1 meter. Okay, the center of mass of the system, we have to find out the distance of the center of mass from 5 kg mass. See, if you want to find the distance of the center of mass from 5 kg, it is always better to choose the position of the 5 kg as the origin. Then the coordinate of the center of mass means the distance of the center of mass from the origin. So if you choose the origin as the location of the 5 kg mass, you will directly get the distance of the center of mass from 5 kg. Okay, so this is the formula. m1 of mass 5 kg is at origin, so its x coordinate is 0. So if you put the values, you will get 10/15, that is equal to 2/3 meter. Okay, see, means it is 0.666 meter. You can convert it into centimeter by multiplying with 100, so it will be 66.66 centimeter, or you can approximate it as 67 centimeter. Okay, now see what is next in this chapter, that is displacement of the center of mass. See, change in position is displacement. Change in position vector is displacement vector. We already have the formula for the position vector of the center of mass. Okay, we have R. Now we have to find delta R. So delta capital R will be m1 delta R1 plus m2 delta R2 divided by m1 plus m2. Delta capital R means change in capital R means change in position vector of the center of mass. It is nothing but the displacement of the center of mass. Okay, again we will get the same beautiful formula. See, center of mass displacement equals m1 s1 plus m2 s2 divided by m1 plus m2. No one can forget this one because all the formula in the same format. Okay, now see, velocity of the center of mass m1 v1 plus m2 v2 divided by m1 plus m2. Okay, now acceleration of the center of mass also same form, m1 a1 plus m2 a2 divided by m1 plus m2. If there are three particles, you have to just extend these to three particles, means it will be m1 a1 plus m2 a2 plus m3 a3 divided by m1 plus m2 plus m3. Okay, now main thing, see, in this case is whenever there is no external force acting on a system. When there is no external force acting on a system, acceleration of the center of mass is 0. Acceleration means change in velocity per second. So acceleration of the center of mass 0 means the velocity of the center of mass will not change when there is no external force. Okay, now let us consider an example based on this. Okay, see, this is also a previous question. Okay, now see, this is to find the displacement, or we have to apply the formula for the displacement of the center of mass. Now, two persons of masses, we have 55 kilogram and 65 kilogram respectively at the opposite ends of a boat of length boat. The length of the boat is 3 meter and weighs 100 kilogram. The 55 kilogram man walks up to the 65 kilogram and sits with him. Children, here initially there are two men on boat, okay, one 55 kilogram and the other 65 kilogram, and the mass of the boat is 100 kilogram. So there are three components in the system, two men and one boat. But initially all the three components are at rest. So initially what would be the velocity of the center of mass? m1 v1 plus m2 v2 plus m3 v3 divided by m1 plus m2 plus m3. But initially all the three bodies are at rest. So v1 0, v2 0, v3 0. So velocity of the center of mass is 0 initially. And as the man walks over the boat, man exerts a force on the boat. And boat will exert an equal reaction on the man. So what happens actually there? See, when the man pushes on the boat with his feet, boat exerts an equal reaction on the man. So man will be moving forward due to this reaction. At the same time, boat with the other man will be moving backwards, okay, due to the action exerted by the man. So the man will move, boat with the other man also will move, but all these take place under the action of internal forces, means forces exerted by the components of the system between each other, okay. So during this motion there is no external force acting on the system along the horizontal. As there is no external force acting on the system, velocity of the center of mass will not change. Initially it was 0, so it will be 0 forever as long as there is no external force. As the velocity of the center of mass remains as 0, what would be the displacement of the center of mass? Definitely it will be 0. So if the boat is in still water, the center of mass of the system shifts by, means we have to find the displacement of the center of mass. Okay, that is of course 0. But children, the most beautiful part of this question is not that, the displacement of the center of mass. It is, see, as one man moves over the boat in one direction, the rest of the system, please listen, rest of the system will be moving in the opposite direction, okay. So when one man gets displaced in a particular direction, then the rest of the system will get displaced in the opposite direction. What would be the displacements of these components? What is the displacement of the man who walks over the boat? And what would be the displacement of the rest of the system in the backward direction? Now children, see, displacement of the center of mass is given by m1 s1 plus m2 s2 divided by m1 plus m2, and it is equal to 0, means the numerator is 0, means m1 s1 plus m2 s2 equal to 0. Okay, so we will get m1 s1, see, this implies m1 s1, this is equal to minus m2 s2, and you can write s1 by s2 equal to minus m2 by m1. See, what is the significance of that negative sign? S1, the absolute displacement of the man who walks over the boat, and S2, the displacement of the rest of the system. Why it's called the rest of the system? Because it, see, there is boat and also another man sitting on the boat. Okay, so S1 and this negative sign is to show that S1 and S2 are in opposite direction. See, man moves from one end of the boat to the other end. Okay, see, initially the initial position of the boat is being shown by red. As the man moves from, see, one end of the boat to the other end, means the man, yeah, see, as the man moves from one end of the boat to the other end, see, during this time boat itself moves backwards. So the final position of the boat is being shown by this broken line, So actually what happens, initially man was at this position, see this position, And finally, see, this is the back end of the boat and this is the front end of the boat. So when the boat is taken as the reference, initially man was at this end of the boat and finally at this end of the boat. But with respect to surroundings, initially the man was here and finally he is here. So this S1 is the displacement with respect to surroundings. Okay, by that time, see the rest of the system, boat with the other man moves back. So this much, see here S2 is the displacement of the rest of the system in the backward direction. Okay, so S1 in the forward direction and S2 in the backward direction. So if we take S1 as positive, then S2 is negative. What is the relative displacement? What is relative velocity of 1 with respect to 2? It is simply V1 minus V2. Similarly, displacement will be S1 minus S2. Acceleration will be A1 minus A2. Okay, so here displacement of the man with respect to the rest of the system will be S1 minus S2, but S2 itself is negative. So S1 minus S2, that is S1 plus S2. Okay, see here this much is S1 and this much is S2. So it is simply the length of the boat. S1 plus S2 equal to length of the boat, and that is equal to 3 meter. Now children, we have S1 by S2 equal to, see, mass of the man who walks over the boat is 55. And the rest of the system means with the other man and the boat, that is 165. So the ratio will be 3:1. Okay, 3 by 1. So S1 and S2 are in the ratio 3:1. Negative sign is only to show that they are in opposite direction. And S1 plus S2 is 3 meter. So how do we get S1 and S2? We have to divide this total displacement S1 plus S2 3 meter into two parts in the ratio 3:1. Means this 3 meter, the complete displacement, is to be divided into 3 plus 1, 4 equal parts. So that each part will be 3 by 4. Okay, of which, see, S1 will be, see, S1 will be 3 parts. When the whole 3 meter is divided into 3 plus 1, 4 equal parts, each part will be 3 by 4. And the displacement of the, see, displacement S1 will be 3 parts. Okay, 3 by 4 into 3. And S2, displacement of the rest of the system will be 1 part. Okay, so S2 equal to 3 by 4 into 1. So if the question is what is the displacement of the actual displacement of the man, means it is 2.25. And by this time, what would be the displacement of the rest of the system? That will be 0.75. Okay, it is not asked here. You have asked, you have to answer here only the displacement of the center of mass. It is very simple and it is 0. Okay. Now see, we have the expression for the center of mass, expression for the velocity of the center of mass of a two particle system. That is velocity of the center of mass VCM equals m1 v1 plus m2 v2 divided by m1 plus m2. See, the same formula can be applied for any system with any number of particles. Okay, if there are 3 particles, you will have to apply m1 v1 plus m2 v2 plus m3 v3 divided by m1 plus m2 plus m3. Now let us consider an example based on this formula. Now see, this is also a previous question. 2 particles which were initially at rest moved towards each other under the action of their mutual attraction or internal attraction. See, here the force of interaction need not be attraction always. Suppose they move under the effect of mutual repulsion. Okay, see, if the system moves under the effect of mutual interaction, it can be repulsion or it can be attraction. See, the forces are only internal. So there will not be any acceleration for the center of mass. Means the velocity of the center of mass will not change, or the center of mass velocity will remain constant as its initial velocity. Okay, now let us, if their speeds are v and 2v at any instant, after some time, initially the 2 particles were at rest. v1 was 0, v2 was 0. So the velocity of the center of mass m1 v1 plus m2 v2, if both v1 and v2 are 0, velocity of the center of mass will be 0. So initially the velocity of the center of mass is 0, and the two particles are moving under the effect of their mutual interaction, means under the action of internal forces alone. So m1 will move, m2 will move, but the velocity of center of mass will not change, means it will remain as its initial velocity 0, means it will remain at rest. Which one? Center of mass. So m1 can move, m2 can move, but center of mass will remain at rest because its initial velocity was 0. Okay. Now the center of mass velocity will be 0. Now see, we have the formula for the position vector of the center of mass. Okay, if the position vectors of the components of the system are given. Okay, and see, here we have two bodies of masses 1 kilogram and 3 kilogram have position vectors. Vectors are given in component form. Okay, we have to find the center of mass, position vector of the center of mass. Here we have the formula for the position vector of the center of mass. Capital R equals m1 r1 plus m2 r2 divided by m1 plus m2. m1 is 1 kilogram and its position vector is given in component form that I have substituted. Okay, m2 is 3 kilogram, its position vector is also given in component form. Okay, so divided by m1 plus m2 means 1 plus 3. Okay, if we multiply, okay, here we have I and here we have minus 3i into 3, that is minus 9i, plus I, that will be minus 8i. Okay, what about the j component? Here we have 2j and here we will have 3 into minus 2, that is minus 6. Minus 6 plus 2 will be minus 4j, minus 4j. And finally we have the z component, that is 1 into k. Okay, and here we have 3k. So 3k plus 1k, that will be 4k. Whole divided by 4. So you will get minus 2i cap minus j cap plus k cap. Okay, minus 2i minus j plus k means this is the correct option. Now let's try another example on center of mass. See, if the linear density, it's given as mass per unit length of a rod of length 3 meter is proportional to x, where x is the distance from one end of the rod. Okay, the distance of the center of gravity of the rod from this end is, okay, see, as this rod is along the x-axis or along the horizontal, its center of mass and center of gravity will coincide. Okay, so center of gravity is same as the center of mass if the body is horizontal. Okay, now see, it is given that mass per unit length varies with the distance from one end of the rod. Okay, now suppose here x equal to 0, so the mass per unit length is 0. As we move from this end to the other end, mass per unit length increases, and mass per unit length, linear mass density, will be maximum at the other end of the rod. Okay, now suppose the mass per unit length is represented by lambda, it is directly proportional to x. Okay, if we replace that proportionality with the equal to, we will have to put a constant of proportionality that I have done here, lambda equal to kx. K is the constant. Okay, so at this end x equal to 0, so lambda will be 0. At this end x equal to 3, so lambda will be 3k. Now that rod can be considered as, see, made up of an infinitely large number of particles with the masses say m1, m2, m3, etc. at position coordinates x1, x2, x3, etc. like that. Now consider, an arbitrary element at a distance say x. See, here you consider an element of a small length dx. See, as this element is at a distance x from this end, the mass per unit length at this location will be kx. That is the mass of an element of length 1. But here we have a small element of length dx. So the mass of that element will be kx into dx. Okay, that stands for m1. Then what would be x1? Its distance from the origin. Its distance from the origin is x. So m1 x1 will be, see, kx into dx, that is m1, and this stands for x1. This is m1 x1. Similarly, we have to take the next element. Then next element, we will have to take all possible elements from x equal to 0 to x equal to 3. And here the x is a continuous variable, not like a 1, 2, 3, like not a discrete variable. Okay, so this is m1 x1. Okay, we have to find m1 x1 plus m2 x2 plus m3 x3 plus m4 x4. Then that is a discrete summation. Here we have to find we have to do the continuous summation. Means we will have to integrate. See, this is an elongated S. See, this is an elongated S. And it stands for summation. Summation means continuous summation. Okay, and this integral is to be evaluated from x equal to 0 to x equal to 3. So this stands for the numerator of that formula for the center of mass. Okay, now we have to get the denominator, that will be the total mass. Total mass. See, what is the mass of each such element? It will be kx, mass per unit length, into length of the element will be dx. So it is kx dx. There will be see a large number of elements with the masses like this kx dx. See, we will have to find the masses of all such elements. Okay, and we will have to add, or we have to do the summation. Here also the summation is continuous, means we will have to integrate from 0 to 3. Okay children, so here we have to integrate kx square. Okay, we have k, both numerator and denominator, so k can be cancelled. When this x square is integrated, we will get x cube by 3, and in the denominator we will get x square by 2. Okay, and see, in the numerator, when we substitute the upper and lower limit, we will get 3 cube by 3 minus 0, and in the denominator 3 square by 2 minus 0. Okay, so that we will get 2 meter, or the center of mass is at 2 meters. So this is the correct answer. Okay, now see, next is moment of inertia. See, it is analogous to mass in linear mechanics. Okay, see, this moment of inertia, it is neither scalar nor vector, it is a tensor. And see, for a point mass, it is defined as the product of mass and square of its perpendicular distance from the axis of rotation. Now suppose a point mass m is rotating about a fixed axis. Okay, then its distance from the axis is r, and its moment of inertia is defined as mr square. Okay, now see, there are certain regular bodies. See, the moment of inertia of all these regular bodies we should know. And see, these regular bodies are, one is ring. Okay, see, first you have to keep in mind that moment of inertia of hollow bodies will be more than the corresponding solid bodies. Okay, means when you take a ring and a disc, ring is hollow, so its moment of inertia will be more compared to the moment of inertia of disc. When you take a hollow cylinder and a solid cylinder, moment of inertia of hollow cylinder will be more. When you take a solid sphere and a spherical shell, moment of inertia of the shell will be more. And one more thing, see, if you keep a large number of rings one over another, you will get a cylindrical shell, or normally people call hollow cylinder. So the moment of inertia of a ring and hollow cylinder will be the same. If you keep a large number of discs one over another, you will get a solid cylinder. So the moment of inertia of a disc and solid cylinder will be the same. Okay, ring and disc. See, moment of inertia of one of these bodies about the symmetric axis. See, the moment of inertia about a symmetric axis of a ring and a disc is, one is mr square and the other is mr square by 2. See, the moment of inertia for one of these bodies, we are considering ring and disc. Moment of inertia of one of these bodies is mr square and the other is mr square by 2. Okay, which one will have more moment of inertia? For the hollow body. So mr square or mr square by 2? For the ring, mr square, because it is greater. Okay, so the moment of inertia of a ring is mr square and that of a disc is mr square by 2. See, moment of inertia of a hollow cylinder is same as the moment of inertia of a ring. So the moment of inertia of a hollow cylinder is mr square, and moment of inertia of a solid cylinder is same as that of a disc, and it is mr square by 2. Now we have got 4 bodies: ring, disc, hollow cylinder, solid cylinder. Next we have to know 2 more bodies. One is spherical shell, or normally people call hollow sphere, and the other is solid sphere. See, the moment of inertia of one of these bodies is 2 by 3 mr square and the other is 2 by 5 mr square. 2 by 3 or 2 by 5, which is greater? 2 by 3. So it must be for the hollow body, or that is the moment of inertia of a spherical shell, 2 by 3 mr square. And the moment of inertia of a solid sphere is 2 by 5 mr square. Okay, so we have see, ring or hollow cylinder, that is mr square, because hollow cylinder can be considered as the combination of a large number of rings, okay, stacked one above another. Okay, now disc and solid cylinder, moment of inertia of disc and solid cylinder is mr square by 2, because solid cylinder can be considered as a large number of discs, okay, stacked one over another. Okay, and the next is hollow sphere. Hollow sphere, or it is a spherical shell, and it is 2 by 3 mr square moment of inertia, and solid sphere it is 2 by 5 mr square. Now see, the moment of inertia of any body can be represented as I equal to mk square, where m is the mass and k is called the radius of gyration. Moment of inertia of any body, if you express like this, then k equal to under root I by m, and that k is called radius of gyration. Okay, now see, in this moment of inertia we have got two theorems. One is parallel axis theorem. See, this can be applied for any rigid body, okay, regular or irregular. Okay, now see, the moment of inertia of a rigid body about any axis. Okay, suppose we want to find the moment of inertia of this. See, this is a body, a rigid body of arbitrary shape. Means this can be applied for any rigid body. What do you mean by rigid? The shape cannot be changed by applying force. That is rigid. Okay. So, see, suppose we want to find the moment of inertia of this body about this axis. This is an arbitrary axis. Okay, what you have to do now? You have to consider an axis parallel to the given axis and passing through the center of mass. So here we have to find the moment of inertia about this axis. So I have taken an axis passing through center of mass and parallel to this axis. That is this one. See, center of mass, see, the moment of inertia about an axis passing through the center of mass, okay, that is represented by I with the suffix cm. Okay, then the moment of inertia about the given axis I is given as I equals ICM plus ma square, where m is the mass of the body and a is the distance between the two axes. Okay, see, let me repeat, these two axes are parallel to each other. Okay, now let us apply this equation for a thin uniform rod. The moment of inertia of a thin uniform rod about an axis passing through its center and perpendicular to its length is ml square by 12. See, suppose this is a meter scale. It can be considered as a uniform rod. Okay, see, this is an axis passing through its center and perpendicular to its length. The moment of inertia about this axis is ml square by 12. And we want to find the moment of inertia about an axis passing through one of its ends and perpendicular to its length. So this is the axis about which we have to find the moment of inertia. This is a parallel axis passing through the center of mass. So we have to apply this formula, I equal to ICM plus ma square. That ICM equals ml square by 12. Okay, and a equals L by 2 here, half of the length of the rod. So L by 2 whole square. So if you add these two, you will get ml square by 3. So the moment of inertia about central axis is ml square by 12, and moment of inertia about an axis passing through one of its ends and perpendicular to its length is ml square by 3. Okay, now see, in this moment of inertia we have one more theorem, that is perpendicular axis theorem. See, this theorem can be applied only for plane bodies. Means it can be applied for a ring, it can be applied for a disc, it can be applied for any plane lamina, but it cannot be applied for a sphere, it cannot be applied for a cylinder, it can be applied only for plane bodies. Okay, now see, suppose the body lies in the xy plane, then x and y axes are perpendicular to each other and they lie in the plane of the body. Okay, they lie in the plane of the body. And see, suppose this is a plane body of arbitrary shape. Okay, this is x-axis, it is in the plane of the body, and this is y-axis, it is also in the plane of the body. And this is the point where these two perpendicular axes intersect. Let me repeat, both the axes are in the plane of the body. Now z-axis is normal to the plane of the body and passing through the point of intersection of these two perpendicular axes. Okay, z-axis. Then perpendicular axis theorem gives Iz equals Ix plus Iy. So the moment of inertia of a plane body about any axis normal to its plane, is the sum of its moments of inertia about two perpendicular axes in its own plane intersecting at the point through which the normal axis passes. Okay, now let us see this is a disk. Suppose we want to find the moment of inertia about a diameter, and suppose the disk lies in the xy plane. So the x-axis is a diameter, and the moment of inertia about that diameter, let it be capital I. See, y-axis also in the plane of the disk, it is also a diameter. So if the moment of inertia about this diameter is I, the moment of inertia about this diameter also must be I, because the disk is symmetrical. Okay, now we already know the moment of inertia about this axis, it is mr square by 2, about an axis passing through its center and normal to its plane. We have the perpendicular axis theorem, Ix plus Iy equal to Iz. Here the disk is in the xy plane and x and y axis intersect at the center of the disk. So Iz is normal to the plane of the disk and passes through its center. So the moment of inertia Iz will be mr square by 2. Okay, Ix equal to I and Iy equal to I, the moment of inertia about a diameter. So we will get 2I equal to mr square by 2, and I, moment of inertia of a disk of mass m and radius r about a diameter is mr square by 4. Now see, next thing that you have to understand in this chapter is the torque. See, it is the turning effect of a force, and torque is analogous to force in linear mechanics. Okay, and see, torque is defined as the moment of the force. Moment means you have to find the cross product with the position vector. Means moment of force means r cross f, where r is the position vector. Moment of linear momentum means r cross p, where p is the linear momentum vector. So moment of means you have to find the cross product with the position vector. Okay, so moment of force means r cross f, that is the torque. Okay, and the angular momentum, it is analogous to linear momentum in linear mechanics. Okay, so angular momentum is moment of linear momentum, means r cross p. Okay, now we have torque is the time rate of change of angular momentum, or tau that represents torque equals dl by dt, where L is the angular momentum. See this formula is analogous to F equal to dp by dt in linear mechanics. Okay, here the quantity analogous to force is torque, and the quantity analogous to linear momentum is angular momentum. Okay, now see, when torque equal to 0, see, when external torque on a system is 0, then dl by dt, differential of the angular momentum, is 0. What does it mean? Angular momentum is constant. So whenever the external torque acting on a system is 0, or when there is no external torque acting on a system, its angular momentum is conserved. So L equal to constant when tau equal to 0. See, it is analogous to the law of conservation of linear momentum in linear mechanics. When there is no external force, linear momentum is conserved. When there is no external torque, angular momentum is conserved. Okay, now we have P equal to mass into velocity. Linear momentum equal to mass into velocity. See, the corresponding relation in rotational motion is angular momentum equals moment of inertia into angular velocity. Okay, and see, dl by dt equal to 0, then L equal to constant. It is called the law of conservation of angular momentum. Okay, now see, when there is no external torque, angular momentum is conserved, or I omega will be constant. So So when PV equal to constant, we can say P1 V1 equal to P2 V2. Similarly, when I omega is constant, we can say I1 omega 1, that is the angular momentum in the first case. This is equal to I2 omega 2, that is the angular momentum in the second case. Okay. Now see, find the torque of a force F equal to minus 3 I cap plus J cap plus 5 K cap, means the force is given in component form. Acting at the point means the position vector is also given in component form. See, we have to find the torque. So tau is given by R cross F. Okay, how do we find the cross product of two vectors if they are given in component form? See, we have to evaluate the determinant. Okay, now see, the first row is being formed by I cap, J cap and K cap, and see, second row is the components of the first vector and third row components of the second vector. Okay, first we have to take this I, that is positive. The second term starting with J will be negative and the next will be positive. Okay, so how do we find that? See, this I is, we have to, how can we decide this I positive or negative? Okay, see, that is the element that belongs to first row and first column. Okay, see, we have to take it positive or negative according to minus 1 raised to I plus J, where the element is in ith row and jth column. Okay, here it is in first row, see, first row and first column. Okay, so I will be 1 and J will be 1. So minus 1 raised to, see, minus 1 raised to 1 plus 1, that is minus 1 raised to 2, that is positive. Okay, now what about this one, J? Okay, this, it is an element in the first row and second column. Okay, so this will be 1 plus 2, first row, second column, 1 plus 2. So minus 1 raised to 3, that is minus 1. See, the first element, see, in see, simple words or in short, we can say first is positive, then negative, then positive, like that. Alternately positive and negative. Okay, now let us evaluate this. See, when you take this I, see, you have to eliminate the row and the column in which that element comes. Okay, so we have to eliminate this row and this column. Okay, the rest we have to multiply like this, 3 into 5. Okay, that is 15, then 1 into 1, that is 1. So 15 minus 1. Okay, now the next this J will be negative, so I have put minus J. Then we have to eliminate this row and the column containing J. Okay, then we have to cross multiply. See, 7 into 5, that is 35. Then minus 3 into 1, that is minus 3. 35 minus minus 3. Okay, see, the next will be K. We have to eliminate the column and the row containing K. Okay, this is positive, this is negative, so this will be again positive, so I have taken plus K. Okay, so if I eliminate this row and this column, okay, so we will get 7 into 1, that is 7, then minus 3 into 3, that is minus 9. 7 minus minus 9. 7 minus minus 9. Okay, so we will get, this is 15 minus 1, that is 14 I cap. Then 35 plus 3, that is 38, so minus 38 J cap plus 16 K cap. Okay, so 14I, so only this one will be true. Okay, now let's try an example based on the law of conservation of angular momentum. See, this is also a previous question. A thin circular ring of mass capital M and radius R is rotating in a horizontal plane about an axis vertical to, it is actually normal to its plane with a constant angular velocity omega. See, now if two objects each of mass small m be attached gently. See, when these two objects are kept at the opposite ends of a diameter, we are not disturbing the system, means there is no external torque acting at that time, so angular momentum will be conserved. So we can write I1 omega 1 equal to I2 omega 2. Initially only the ring is rotating, its moment of inertia is mr square. See, I1 omega 1 equal to I2 omega 2. Initially only the ring, so the moment of inertia is mr square and angular velocity is omega. See, finally there is ring and also two point objects at the opposite ends of a diameter. So the total moment of inertia will be moment of inertia of the ring plus moment of inertia of these 2-point objects. See, the moment of inertia of this object will be m into square of its distance from the axis, perpendicular distance from the axis. So it will be small m into r square, this also small m into r square, and moment of inertia of the ring will be capital M into capital R square. So we will get capital M R square, small m into capital R square, again small m into capital R square. So R square is common throughout. So we can cancel R square. So on the right side we will get capital M plus 2 small m, and omega dash, the final angular velocity, will be capital M divided by m plus 2m into omega. Okay, capital M divided by m plus 2m. Okay, so this will be the right choice. Okay, see, this is a typical question. You can expect this type of questions see for the coming NEET exam also. Okay, next equations of motion. See, we have studied many equations and formulae in linear mechanics. There will be corresponding equations and formulae in rotational mechanics also. See, we have studied V equal to U plus AT, where V is the final velocity, U is the initial velocity, and A is the constant acceleration. See, the corresponding relation in rotational mechanics is omega equals omega 0 plus alpha t. Omega is the final angular velocity, omega 0 is the initial angular velocity, and alpha is the constant angular acceleration. We have S equal to ut plus half at square. S is the linear displacement. Corresponding equation in rotational motion is theta equals omega 0 t plus half alpha t square, where theta is the angular displacement. In linear mechanics, we have V square equal to U square plus 2as, and corresponding equation in rotational motion is omega square equal to omega 0 square plus 2 alpha theta. Okay. And similarly, we have displacement during the nth seconds. Okay, when a body moves with a constant acceleration. See, in linear mechanics, we have studied S with the suffix n, displacement in the nth seconds. That is equal to U plus A by 2 into 2n minus 1. Similar equation we can write in rotational motion, that is theta with the suffix n equal to omega 0, initial angular velocity, okay, plus alpha by 2 into 2n minus 1. Okay. See, in linear mechanics we have studied, if a body starts from rest and moves with a constant acceleration. Okay, see, if the body starts from rest and moves with a constant acceleration, means when u equal to 0, s with the suffix n will be a by 2 times 2n minus 1. Okay, and see, similar relation, see, in rotational mechanics, okay, when omega 0 equal to 0, means initially if the rigid body is at rest and it starts rotating with a constant angular acceleration, then the ratio of then the displacement in nth second will be alpha by 2 into 2n minus 1. So whatever equations we have studied in linear mechanics, similar equations we can apply in rotational mechanics also. Now, if a body starts from rest and moves with a constant acceleration along a straight line, then see, ratio of displacements in successive equal intervals of time will be 1:3:5:7, like that. Similarly, if a rigid body starts from rest and rotates with the uniform angular acceleration, then the ratio of angular displacements in successive equal intervals of time will be again 1:3:5:7. See, the same thing we can apply in the reverse order for a body comes to rest with uniform retardation. See, when a body starts from rest and moves with a constant acceleration, then a ratio of displacements will be 1:3:5:7. But if a body comes to rest with a uniform retardation, then ratio of displacements in successive equal intervals of time will be, say, if there are 4 intervals, 7:5:3:1. when it comes to rest with uniform retardation. See, the same relation we can apply in the reverse order. Okay, similarly we can apply in rotational motion also. If a body comes to rest with uniform angular deceleration or angular retardation, okay, then the ratio of displacements in successive equal intervals of time will be 7:5:3:1 if there are 4 intervals, and 5:3:1 if there are 3 intervals, like that. Okay, now see, next we have energy, that is the kinetic energy, or see the translational kinetic energy, that is half mv square, and it is also equal to p square by 2m, where p is the linear momentum. So this is an important relation, kinetic energy expressed in terms of linear momentum, p square by 2m. Similar relation we can have in rotational motion also, that is the rotational kinetic energy. This is E. Here it is translational kinetic energy. So if we want, we can give a suffix E with the suffix T, and this is rotational kinetic energy, that is E with the suffix R. Okay, here it is half mv square. Mass and linear velocity, corresponding quantities in rotational motion are moment of inertia and angular velocity. So it will be half I omega square. And here we have p square by 2m, where p is the linear momentum and m is the mass. Corresponding quantities in rotational motion are angular momentum and moment of inertia. Angular momentum is capital L and moment of inertia is I. So we will have L square by 2I. Okay. See, in linear mechanics we have force F is the time rate of change of linear momentum, dp by dt. Okay. Corresponding relation we have in rotational mechanics, that is tau equal to dl by dt, time rate of change of angular momentum equal to torque. And see, F equal to mass into acceleration. Similar relation in rotational motion, torque equal to I alpha, where I is the moment of inertia, that is analogous to mass in linear mechanics, and alpha is the angular acceleration, it's analogous to linear acceleration. Okay, now we have work done equal to dot product of force and displacement. In rotational motion, it will be the dot product of torque and angular displacement, tau dot theta. Again, angular displacement is also a vector, torque is also a vector. Okay, and see, work done is also equal to change in kinetic energy. In rotational motion, it will be equal to the change in rotational kinetic energy. Okay, similar relation. And impulse, it's called a linear impulse, that is equal to F delta t, and it is equal to change in linear momentum. Corresponding relation in rotational mechanics is again it is the angular impulse. Here I stands for angular impulse, that is equal to tau into delta t, and that is equal to change in angular momentum. Now children, here we have a typical example. This is also a previous question. The moment of inertia of a body about a given axis is 1.2 kilogram meter square. Initially the body is at rest, so omega 0 equal to 0. In order to produce a rotational kinetic energy of 1500 joule, an angular acceleration of 25 radians per second square must be applied about that axis for a duration of. Okay, now see, we can apply omega equals omega 0 plus alpha t. It is corresponding to v equal to u plus at in linear mechanics. So omega equal to omega 0 is 0, so omega will be equal to alpha t. See, translational kinetic energy is half mv square. Corresponding relation in rotational motion is half I omega square. See, this is the rotational kinetic energy. Let me see E with the suffix R. Okay, here we have got omega equal to alpha t. So the rotational kinetic energy will be half into I into alpha t whole square. Okay, and alpha t will be under root 2 rotational kinetic energy, okay, divided by moment of inertia. And rotational kinetic energy is given as 1500. So it will be 3000 divided by 1.2 or 30,000 divided by 12. That 30,000 divided by 12 can be, see, if we divide both the numerator and the denominator by 3, we will get 10,000 divided by 4. 10,000 is a perfect square, its root is 100. 4 is also a perfect square, its square root is 2. So 100 over 2, that will be 50. So alpha t equal to 50. And t will be, see, 50 divided by alpha. Angular acceleration alpha is given as, see, 25 radians per second square. So we will get t equal to 2 seconds. Beautiful question. Okay, so 2 seconds. Next we have angular momentum and rotational kinetic energy. See, linear momentum is represented by small p and it is equal to the product of mass and linear velocity. Corresponding relation in rotational motion is angular momentum L equal to I omega, where I is the moment of inertia and omega is the angular velocity. Translational kinetic energy half mv square and rotational kinetic energy is half I omega square. See, we can express the translational kinetic energy in terms of linear momentum, so that ET means energy, E stands for kinetic energy and T for translational. So translational kinetic energy is P square by 2m, where P is the linear momentum. Corresponding formula in the rotational motion is rotational kinetic energy E with the suffix R, that is equal to L square divided by 2I. See, from this we will get linear momentum equal to under root 2 into mass into translational kinetic energy. So, similar relation in rotational motion, the angular momentum L equal to under root 2 into moment of inertia into rotational kinetic energy. Okay, now let us try an example based on this. Two bodies have their moments of inertia capital I and 2I. See, this is also a previous question. About their axis of rotation, if their kinetic energies of rotation are equal, means two bodies are having equal kinetic energy, we have to find the ratio of their angular momenta. See, linear momentum P equals under root 2m into translational kinetic energy. Similar relation we can write in rotational motion, L equal to under root 2 moment of inertia and rotational kinetic energy. We have two bodies. Okay, as we move from one body to the other, there is no change in rotational kinetic energy, or rotational kinetic energy remains same, or we can take it as constant. So, see, this is constant, 2 is also constant, so we can say angular momentum directly proportional to square root of the moment of inertia in this particular case. So, L1 by L2 will be under root I1 by I2. And see, the moment of inertia are given as I and 2I, so it will be I by 2I or 1 by root 2. Okay, so 1 by root 2 means 1 is to root 2. Okay, now see, we have another example, and that is to find the angular velocity, and it is based on the angular impulse is equal to change in angular momentum. Okay. A constant torque, 1000 Newton meter, turns a wheel of moment of inertia 200 kilogram meter square about an axis through its center. The angular velocity after 3 seconds is. See, we have the torque and we have the time for which the torque acts and also the moment of inertia. Okay, suppose the wheel is turned from rest. Okay. And see, delta omega will be final angular velocity omega, that we have to find out, minus initial angular velocity 0. Okay, see, F delta t, linear impulse equal to change in linear momentum m delta v. Similarly, angular impulse tau delta t equal to I into delta omega, and delta omega equal to final angular velocity omega minus initial angular velocity. As the wheel is initially at rest, its initial angular velocity 0. Okay, delta omega will be tau delta t divided by I. Okay, so omega will be tau is 1000, delta t is 3 seconds, and moment of inertia is 200. Okay, so this will be 1000 divided by 200, that is equal to 5. 5 into 3 will be 15. So 15 radians per second. So this is the correct option. Okay. Now children, it is the time to discuss rolling. Okay, now see, I have a body that is cylindrical in shape. Okay, a body which can roll. Okay, now see, if this body is moving like this, see, moving like this. See, if it is moving like this, then it is in translational motion, or let us say it slides. It is in sliding motion, or it is in translational motion. See, if it rotates here, means it is not moving translationally. Then see, it rotates. See, this motion is called rotation. Okay, and if the body rotates and at the same time moves translationally. Means like this. It rotates and at the same time moves translationally. Okay, then it is said to be rolling. When a body is in pure rolling, the rotational motion and the translational motion are in a balanced condition. Then see, V will be equal to omega R in pure rolling. V equal to omega R. See, if V is greater than omega R, then translational motion dominates. If omega R greater than V, then rotational motion dominates. If V equal to omega R, then the body is said to be in pure rolling. The rotation and the translational motion are in a balanced condition. Okay, now see, where a rolling body will possess, of course, translational kinetic energy half mv square and also rotational kinetic energy half I omega square. When a body is in pure rolling, V will be equal to omega R. So let us see, E with the suffix T, that is equal to half mv square. That V can be replaced by omega R. So we will get half m r square omega square. And rotational kinetic energy is half I omega square. That I can be replaced by mk square, where k is called the radius of gyration. Okay, half mk square. So if you find the ratio of rotational kinetic energy to the translational kinetic energy, you will get k square over r square. Okay, now see, first we have studied the normal, common translational kinetic energy, half mv square. Later we have studied half I omega square. Okay, first we have studied ordinary kinetic energy, half mv square, translational kinetic energy. See, this E with the suffix T, that is the translational kinetic energy, or see, let us simply say the ordinary kinetic energy. And it corresponds to the square of the ordinary radius. Okay, that is r square. See, this rotational kinetic energy we have studied later, and this k, that is the radius that we have studied later, it is called the radius of gyration. So rotational kinetic energy corresponds to square of the rotational radius, let us say, it's called the radius of gyration. And common kinetic energy corresponds to the square of the common radius square, r square. Okay, rolling body possesses both. Okay, fine. Now see, this ratio k square by r square is a very important ratio. And what is that ratio? See, any body capable of rolling will have a radius. And the moment of inertia of that body will be, see, something into mr square. For example, a ring and hollow cylinder, 1 mr square. So the coefficient of mr square is 1. Disc or solid cylinder, half mr square. So in the expression for moment of inertia, the coefficient of mr square is half. For a spherical shell, the moment of inertia is 2 by 3 mr square. So the coefficient of mr square in the expression for moment of inertia of a spherical shell is 2 by 3. Okay, for solid sphere it is 2 by 5 mr square. See, in the expression for the moment of inertia of a rolling body, the coefficient of mr square is the ratio k square by r square. And the reciprocal of that ratio will give you the r square by k square. Okay, now we have see these 6 regular bodies that we have to study. See, ring and hollow cylinder can be considered as the combination of a large number of identical rings. Okay, so the ring and hollow cylinder will have the same moment of inertia. So they will have the same ratio k square by r square, and it is equal to 1 because their moment of inertia is 1 mr square. See, disc and solid cylinder is simply the assembly of a large number of identical discs. So both these bodies are having the same moment of inertia, it is half mr square. So the ratio k square by r square is half. For a spherical shell, or let us say the hollow sphere, the moment of inertia is 2 by 3 mr square and the ratio k square by r square is 2 by 3. And for solid sphere, it is 2 by 5. Okay, now that ratio is very important. Now let us go to the next, see, that is kinetic energy. See, as I have told you earlier, a rolling body will possess both translational kinetic energy half mv square and rotational kinetic energy half I omega square. And the total kinetic energy will be the sum of these two. So a common question that you can expect is what fraction of its total kinetic energy is due to rotational motion. and what fraction is due to translational motion. Okay, now let us see rotational kinetic energy divided by translational kinetic energy will be equal to square of the radius of gyration divided by square of the normal radius. Okay, normal kinetic energy corresponds to normal radius square. Rotational kinetic energy corresponds to rotational radius square. Okay, that is the radius of gyration. Okay, now see here ER divided by ER plus ET. Corresponding to ER, you can put K square. Corresponding to ER plus ET, you can put K square plus R square. Now see, when you take this numerator K square into the denominator, it will come in the denominator of the denominator. Okay, means in the numerator there will be 1 and denominator becomes K square plus R square by K square. So we can write 1 plus R square by K square. See, for any body, K square by R square is the coefficient of mR square in the expression for moment of inertia, and this will be R square by K square is the reciprocal of that ratio. Okay. Now see, so we have rotational kinetic energy divided by total kinetic energy. See, E with the suffix T stands for translational. E with the suffix R stands for rotational. Simply E means without any suffix, that represents total. So here rotational by total means the fraction of total energy that is due to rotational motion. Okay, so that is 1 divided by 1 plus R square by K square, and we have the total energy E equals ER into 1 plus R square by K square. ER into 1 plus R square by K square. Okay, and see what is ER, that is half I omega square into 1 plus R square by K square. Okay, next what fraction of the total kinetic energy is due to translational motion? We have ET by ER equal to R square by K square. So ET translational by translational plus rotational. So corresponding to translational you can write R square, and corresponding to translational plus rotational you can write R square plus K square. Okay, now take this R square from the numerator to the denominator, so it will be R square plus K square whole by R square, so it will be 1 plus K square by R square. Okay, so what fraction of the total energy is due to translational? Means ET by total means without suffix here. Okay, that is 1 divided by 1 plus K square by R square. Okay, see, ER by ET I have got 1 divided by 1 plus R square by K square, and here is ET by total, that is 1 by 1 plus K square by R square. Okay, and total energy that is without any suffix, E equal to translational energy into 1 plus K square by R square, and translational energy is half mv square into 1 plus K square by R square. Children, you may be confused or you may not be able to remember whether, see, this ratio is K square by or K square by R square or R square by K square. That may be your confusion. Okay, so I will give you, see, yeah, here we have rotational by total. So if we simplify this expression, okay, if we simplify this expression, rotational kinetic energy is in the numerator, so K square should come in the numerator if we simplify this. If K square has to come in the numerator, then it must be in the denominator of the denominator. Then only see, you will get it in the numerator when you simplify it. Okay, and here we have translational in the numerator. So when you simplify this, R square should come in the numerator. See, R square will come in the numerator only if it is in the denominator of the denominator. Means it must be K square by R square. Okay, then I will tell you one more thing. Okay, see, this capital is the total energy. Means it must be the sum of rotational kinetic energy plus translational kinetic energy. Children, see, ER, that is the rotational kinetic energy, into 1, that is the first term if you open the brackets. ER into 1, that is the rotational kinetic energy. So the next term should be the translational kinetic energy. Rotational, okay, corresponds to K square, and translational corresponds to R square. So here next term, second term, see, ER into R square by K square. Means what we are doing, see this rotational kinetic energy will be divided by K square. When rotational kinetic energy is divided by K square, it gets normalized. Means we will remove the flavor and it will become a neutral. It will become kinetic energy without any flavor. And see, when ER is being divided by K square, it gets neutralized. After that, it is being multiplied by R square, means we are providing the flavor of translational kinetic energy. Okay, second term should be translational. And here we have, see, half mv square into 1. Definitely it is half mv square, that is the translational kinetic energy, and next term should be rotational. When this half mv square is being divided by R square, it will get neutralized. We have removed the flavor. And now when it is being multiplied by K square, we have put the flavor of rotational. Okay. Now let us see a body which rolls down a rough inclined plane. A body can roll down or initiate rolling. See, if a body is in rolling motion, it can continue its rolling. Please listen, it can continue its rolling over a frictionless surface. But a body can initiate rolling or starts rolling only if the surface is rough, because only the friction can provide the torque. Okay. Now see, here a body rolls down an incline. So this is the expression for the acceleration of a body rolling down an inclined plane. G sin theta divided by 1 plus K square by R square. Here also we have that wonderful ratio K square by R square in the denominator. Okay. And see, when body is released, as it rolls down, whatever equations you have studied for translational motion, for a body moving along a straight line, all those equations you can apply here. Only thing is that acceleration is G sin theta over 1 plus K square by R square. Okay, so initially suppose the body starts from rest, and see the length of the path, let it be S. So S equal to ut plus half at square we can apply. U0, ut0. So S equal to half at square. S equal to half at square, and T we will get under root 2S by A. S equal to half at square. From that you will get T equal to under root 2S by A. And next week you can apply V square equal to U square plus 2AS. Again body starts rolling from rest. So U0, U square 0. So V square equal to 2AS, and V will be under root 2AS. That is the speed of the body when it is at the bottom of the incline. Okay. Now children, okay, see, the acceleration of a body with which it rolls down a rough inclined plane is G sin theta divided by 1 plus K square by R square. Suppose we have 6 bodies, a ring, a hollow cylinder, a disc, a solid cylinder, okay, then spherical shell and solid sphere, 6 rigid bodies. Suppose all the bodies are released from the same incline, from the top of the same inclined plane. Which one will reach the bottom first? Which body will reach the bottom next? Which body will reach the bottom last? Let us see. See what is this acceleration? See, this is the time taken by the body to reach the bottom. See, in the expression for time, see, acceleration is in the denominator. So if the acceleration is more, time will be less. Okay. Now see. This is the expression for acceleration, and in the expression for acceleration, this K square by R square is in the denominator. K square by R square is in the denominator. So children, please listen. See, K square by R square is in the denominator. Okay, let me pull this down. Right. Now see, K square by R square. Okay, K square by R square is in the denominator. If this K square by R square is smaller, if K square by R square is smaller, then acceleration will be more. Acceleration will be more, because in the expression for acceleration, K square by R square is in the denominator. Now when acceleration is more, time will be less. Okay. Now see, time will be less. Now children, let us combine these two. Okay, see, let us combine these two, right? These two you can combine. When k square by r square is less, time will be less. Time less means body will reach the bottom first. When time is minimum, body reaches the bottom first because all the 6 bodies released simultaneously from the top of the incline. Okay. Now see, when k square by r square is minimum, time will be minimum. Solid sphere, moment of inertia is 2 by 5 mr square, and the ratio k square by r square is the coefficient of mr square in the expression for moment of inertia. As its moment of inertia is 2 by 5 mr square, its k square by r square is 2 by 5, and it is equal to 0.4. Okay, now we have disk or solid cylinder, and its moment of inertia is half mr square. The ratio k square by r square is half, and it is 0.5. Now we have hollow sphere. The moment of inertia is 2 by 3 mr square, and its ratio 2 by 3 is 0.66 k square by r square. Okay, and ring or hollow cylinder, moment of inertia is 1 mr square, so k square by r square is 1. So among these bodies, k square by r square ratio is minimum for the solid sphere. So this will reach the bottom first. Okay, this reaches the bottom first, right? Now see, after that see k square by r square, then 0.5, so this will reach the bottom second. Then it comes 0.666, this will reach the bottom third, and finally, okay, last, ring and hollow cylinder. Ring and hollow cylinder will reach the bottom simultaneously. Disk and solid cylinder reach the bottom simultaneously. Okay, right. Now see, suppose a body rolls down an inclined plane from rest from a height h. Initially the body is at rest, so it possesses only the gravitational potential energy. When it reaches the bottom, the decrease in gravitational potential energy will be converted as kinetic energy. Okay, body is released from here. Initial gravitational potential energy is mgh, and when it reaches the bottom, suppose its velocity is v, so the total kinetic energy as it rolls down will be half mv square into 1 plus k square by r square, that we have studied. This is the total kinetic energy at the bottom, that is equal to potential energy at the top. So from here we will get v equal to under root 2gh divided by 1 plus k square by r square. This is the speed with which the body reaches the bottom of the incline. Okay, so here when k square by r square is small, velocity will be more. So k square by r square is minimum for solid sphere, so it reaches the bottom with the maximum speed. K square by r square is maximum for ring or hollow cylinder, so ring or hollow cylinder reach the bottom with the minimum speeds. Okay, now see, instead of rolling down the incline, suppose a body rolls up the incline. So the acceleration g sin theta divided by 1 plus k square by r square, as it rolls down, the same will be the retardation here. Okay, when it rolls up the incline, retardation will be g sin theta divided by 1 plus k square by r square. Okay, and the total kinetic energy at the bottom will be converted as gravitational potential energy at the top. Okay, so mgh, potential energy at the top, equal to half mv square into 1 plus k square by r square, that is the total kinetic energy at the bottom. Okay, so we will get h equal to v square by 2g into 1 plus k square by r square. So this is the maximum height up to which the body rolls up the incline. Okay, that also see, proportional to k square by r square. When k square by r square is more, the height up to which the body can roll will be more. Means if all the 6 bodies are rolled up the same incline with the same initial speed, ring and hollow cylinder will reach the maximum heights because those two bodies are having maximum k square by r square. Children, here also see, in all these expressions we have the ratio k square by r square. Okay, now children, let us compare sliding motion and rolling motion. Okay, now see, suppose this body slides like this, then it is in translational motion. That is the case we have studied earlier. And rotation or rolling means the body will be moving like this. Body will be moving like this. That we have studied later, and it is considered as the second case here. Okay, what we have studied earlier as the first case, what we have studied later as the second case. Okay, so when a body slides down the plane, acceleration is simply g sine theta. It is assumed to be frictionless. And when it rolls, okay, when it rolls, it is friction. It is with friction. Okay, only with friction the body can roll down. Okay, so A2 equal to g sine theta divided by 1 plus k square by r square. This is the acceleration when the body rolls down, and this is the acceleration when the body slides down. Okay, now see t, the time taken by the body to reach the bottom, that is equal to under root 2s by a when the body slides or when it rolls. In both the cases, body starts from rest. In both the cases, body has to cover the same displacement, yes. So for both the cases, see, this will be valid, this one. And in both the cases, 2s is the same. The displacement it covers is the same. So t, let us say t directly proportional to 1 by root a. Okay, so here we can say t proportional to 1 divided by root a. Okay, 1 by root a. So t1 by t2, that will be equal to a2 by a1 under root. Okay. So a2 by a1 divided by, see this a2 we have to divide with the a1 g sine theta. So we will get 1 divided by 1 plus k square by r square under root here. Okay, 1 divided by 1 plus k square by r square. Now when the body reaches the bottom, its speed will be v equal to root of 2as. We have to consider two cases: when body slides down the incline, when body rolls down the incline. See this v equal to root of 2as we have got from v square equal to u square plus 2as, in which u is 0. Initially body starts from rest, so u square 0. So v square equal to 2as and v will be equal to root of 2as. See, in both the cases, means when it slides or when it rolls, these 2 and s are the same. So we can say v directly proportional to root a. So v1 by v2 will be root of a1 by a2. Means g sine theta divided by g sine theta divided by 1 plus k square by r square, that will be under root 1 plus k square by r square. Okay. Now see this k square by r square we know for ring and hollow cylinder it is 1. For disc and solid cylinder it is 1 by 2. For a hollow sphere or spherical shell it is 2 by 3. For a solid sphere it is 2 by 5. Okay. And see, now suppose a body moves up the incline. If it slides along the incline upwards, then half mv square kinetic energy at the bottom equal to mg h1. H1 is the height up to which the body goes up. In the first case means when it slides. So h1 equal to v square by 2g. So this is the maximum height up to which it can go if it slides up the incline. If the body starts with the same initial velocity and rolls up the plane, then this is the kinetic energy at the bottom equal to potential energy at the top, and this is not h1, it must be h2, right? Okay, in the second case it must be h2. Okay, so this is h2 and this is h2. So h2 equal to v square by 2g into 1 plus k square by r square. So a body will go higher if it rolls up the incline. Okay, compared to the case in which it slides up the plane. Okay, now next let us see. Yeah, we have a wonderful example. A disc of radius 2 meter and mass 100 kilogram rolls on a horizontal floor, not over the inclined plane. Its center of mass has speed of 20 centimeter per second, that we can easily convert into meter per second, that is 0.2 meter per second. How much work is needed to stop? Means change in kinetic energy. Initially it possesses some kinetic energy, that will be half mv square into 1 plus k square by r square. Finally when it stops, its kinetic energy will become 0. So the change in kinetic energy will be equal to initial kinetic energy and it is equal to the work done. Okay, and here the body is a disk, its moment of inertia is half mr square, so the wonderful ratio k square by r square is 1 by 2. Okay, so this is the kinetic energy, half mv square, half mass is 100 kilogram, velocity is 0.2, and 1 plus k square by r square is 1 by 2. So here half I have written, 100 I have written, 0.2 square is 0.04, and 1 plus 1 by 2 is 3 by 2. 100 into 0.04 will be 4. Okay, in the denominator we have 2 into 2, 4. Okay, so ultimately we will get 3 joule, right? So the answer 3 joule. Now children, see, we have another wonderful example here, that is a solid cylinder of mass 2 kilogram and radius 50 centimeter rolls up an incline plane of angle of inclination 30 degree. The center of mass of the cylinder has a speed of 4 meter per second, that is v. The distance travelled by the cylinder on the inclined surface will be. Okay, so there are two methods to solve this question. See, actually we want to find the length of this path. See the length of this path. Okay, as the body moves from here to here, okay, it goes to a height h. So potential energy increases by mgh. This is the kinetic energy at the bottom, that is equal to potential energy at the top. And we will get h equal to v square by 2g into 1 plus k square by r square. And here it is a solid cylinder. So k square by r square is 1 by 2. 1 plus 1 by 2 will be 3 by 2. Okay, 3 v square by 2 into 2g means 3 v square by 4g. Okay, we have, what is the velocity? Velocity is given as 4 meter per second. Okay, so here we have 4 square in the numerator and 1 4 in the denominator. So 1 4 from the numerator and 4 from the denominator can be cancelled. So in the numerator what remains? 3 into 4, that is 12. And in the denominator what remains? G, that is 10. 12 by 10, that is equal to 1.2. That is the height. But we want to find the length of this incline. Children, here we have, this is a right angle triangle, and this is the angle theta. H is the opposite side and S is the hypotenuse. So H by S is sine theta. H by S is sine theta. Okay, so H by S, H divided by S, this is equal to sine theta means sine 30. Okay, that is equal to 1 by 2. So S will be 2H. S will be 2H. H is 1.2. So S will be 1.2 into 2, that is 2.4. Okay, here we have 2.4, right? So S equal to H by sine 30. Sine 30 is 1 by 2. H by 1 by 2 means 2H. Okay, and next, see, using the equations of motion, v square equal to u square plus 2as, we can again find. See, when body rolls up the incline, I have told you, g sin theta divided by 1 plus k square by r square is the retardation. Okay, theta here is 30 degree. So in the numerator we will get g into 1 by 2. As the body being a solid cylinder, yes, solid cylinder, k square by r square is 1 by 2. So in the denominator we will have 1 plus 1 by 2, that is 3 by 2. Okay, so see, in the numerator there is 1 by 2, in the denominator also there is 1 by 2. So 1 by 2 can be cancelled, and what remains? It is g by 3. That is the uniform retardation the body experiences as it rolls up the incline. Okay, now let us apply v square equal to u square plus 2as. As it experiences retardation, it will be minus 2as, and at the final position its velocity falls to 0. So 0 equal to u square minus 2as, or 2as is equal to u square, and yes, we will have u square by 2a. Okay, so it will be 4 square divided by 2 into acceleration. We have got g by 3, or g we can take 10 by 3. Okay, so this 3 will go to the numerator. Okay, and in the denominator we have 2 into 10. Okay, in the numerator there is 4 square, that is 16 into 3, that is 48. 48 divided by 2 will be 24, divided by 10 will be 2.4 meter. The beautiful answer we have here, 2.4 meter. Okay, now let us try what we have next. A solid sphere is rolling motion. In rolling motion, a body possesses translational kinetic energy k with the suffix t, as well as the rotational kinetic energy K with the suffix R simultaneously, the ratio KT is to KT plus KR. Means translational to total we have to find out. Translational to total. Translational divided by total. Translational corresponds to R square. Total corresponds to R square plus K square. So we have R square divided by R square plus K square. Now you can take that R square in the numerator to the denominator. So it will come in the denominator of the denominator. Means it will be 1 divided by R square plus K square by R square. So 1 divided by 1 plus K square by R square. Here we have 1 divided by 1 plus K square by R square. Now it is a solid sphere. Moment of inertia is 2 by 5 mr square. Okay. So K square by R square is 2 by 5. In the denominator we have 1 plus 2 by 5. That is 7 by 5. 1 by 7 by 5 will be 5 by 7. Okay, that we have here 5 by 7. So the answer must be 5 is to 7. Okay, now let us check what we have next. Okay, a disc and a sphere of same radius but different masses roll off on two inclined planes of the same altitude and length. Which one of the objects get to the bottom of the plane first? That we have discussed earlier. Okay, we have see, all the bodies are released from the same incline, from the top of the same incline, and all start from rests. Okay, and all rolls down without slipping. So S equal to ut plus half a t square u0 ut0. So half a t square and t will be under root 2s over a. Okay, so this is the see, 2s divided by a will be g sin theta by 1 plus k square by r square will come to the numerator. Okay, 1 plus k square by r square. So the time will be minimum in case of a body with minimum k square by r square. Now let us write the ratio k square by r square for different bodies. Disc k square by r square is half and it is 0.5. For sphere it is 2 by 5 and it is equal to 0.4. So k square by r square is minimum for a sphere. So it reaches the bottom first. Both reach at the same time, depends on their masses, but sphere reaches the bottom first. Okay, now children, let us see what we have next. This is the ratio of the accelerations for a solid sphere rolling down an incline of angle theta without slipping and slipping down without rolling. Okay, so first rolls, then slips. Okay, here see, earlier we have taken sliding as the first case and rolling as the second case, but in this particular question rolling is the first case and sliding is the second case. Okay, now rolling without sliding, without slipping, that is a1 equal to g sin theta divided by 1 plus k square by r square, and slipping without rolling, that is simply g sin theta. Okay, so this g sin theta can be replaced by a2. Okay, a1 equal to g sin theta can be replaced by a2. So we will get a1 equal to a2 by 1 plus k square by r square. Here the body is a solid sphere. K square by r square is 2 by 5. So 1 plus 2 by 5, that is 7 by 5 in the denominator. So a1 will be 5 by 7 a2 and a1 by a2 will be 5 by 7. Okay, we have to find the ratio of a1 and a2. So it will be 5 by 7 means it must be the first choice. Okay. Now children, see, what is angular momentum? See, this can be answered in two different ways. Angular momentum equals linear momentum into lever arm. Lever arm means perpendicular distance to the line along which the linear momentum is acting from the axis. Okay, that is the lever arm. Perpendicular distance from the axis to the line along which the linear momentum is acting. Okay, now so this linear momentum into lever arm, that is angular momentum L, and this is called the physical meaning of angular momentum. Okay, now what is angular momentum? We can answer that question in a different way. That is, angular momentum L equals 2m into delta A by delta T, that is the area divided by time, or it is called aerial velocity. Or angular momentum equals 2m, 2 into mass of the body into aerial velocity. And this is called geometrical meaning of angular momentum. Okay, now children, see, we have the law of conservation of angular momentum. See, delta A by delta T, that is the aerial velocity, equal to L, angular momentum, divided by 2m, 2 into mass. Okay, and when tau equal to 0, when there is no external torque, dl by dt equal to 0, means differential of angular momentum is 0, means angular momentum is constant. So L equal to constant we will get. Whenever there is no external torque acting on a system, angular momentum is constant. What does it mean? See, delta A by delta T, aerial velocity equal to L by 2m. 2 is already constant. It is a universal constant 2. And m, mass of the body, is also constant. It does not change with the time. And when there is no torque, L is also constant. So when there is no torque, L constant, 2 constant, m constant, means L by 2m constant, or aerial velocity is constant. Okay, now let us see a wonderful example based on this. Now consider the planetary motion. Okay, every planet revolves around the sun in an elliptical orbit under the effect of gravitational attraction between the planet and the sun. Okay, now see, this is the position of the sun, and suppose the planet is here. Okay, see, the planet is revolving about an axis passing through the sun. So this is the axis about which the planet is revolving. Axis is like this. Now if the force acting on the planet had been along this direction, then the perpendicular distance or lever arm from the axis to the line along which the force is acting, that is this much. Okay, now see, if the force on the planet had been along this direction, then the perpendicular distance from the axis would have been this much. But the gravitational force is a central force. It acts along the line joining the two bodies. Okay, line joining the centers of the two bodies. So in this case, the gravitational attraction exerted by the sun on the planet is along this direction. So it passes through the axis. So the lever arm is 0, torque is 0. So angular momentum is constant and aerial velocity is constant. That is the reason why radius vector drawn from the sun to the planet sweeps out equal areas in equal intervals of time. Okay, children, before I conclude, let me give you one more wonderful idea. Okay, suppose we kick a ball with, say, maximum speed. So initially it will be sliding with the sliding fast. So the frictional force will be acting on that sliding body, and that frictional force will oppose the translational motion and favors the rotational motion. Let me repeat. When a ball is kicked, it will be initially sliding with a starts with an initial velocity, say v0, say v with suffix 0. Okay, so a frictional force will be acting on that ball. You might have noticed that, see, any ball, before it comes to rest, it starts rolling. Any ball, before it comes to rest, need not be ball or ring or disc or anything. Okay, if see, if it starts with the sliding, before it comes to rest, it starts pure rolling. Now the question is, what would be its velocity when it starts rolling before it comes to rest? Okay, now suppose the body starts with the velocity v0, I have told you, no? Okay, so the body starts pure rolling when its velocity falls to v0 divided by 1 plus k square by r square. Okay, when a body falls to, when the velocity of the body falls to v0 divided by 1 plus k square by r square, it starts pure rolling. Suppose a ring is thrown with an initial velocity v0. Initially it will be sliding. The frictional force discourages translational motion, encourages rotational motion. So the friction provides angular acceleration, linear retardation. Linear velocity goes on decreasing, angular velocity goes on increasing. At a certain stage, these two will become balanced. V will become equal to omega r. Body starts pure rolling. At that moment, when the body starts pure rolling, its velocity will be V0 by 1 plus k square by r square. If it is a ring, its moment of inertia is 1 mr square. So k square by r square is 1. So its velocity will be V0 by 1 plus 1 means 2. Means a ring will start pure rolling when its velocity falls to half of its initial velocity. Okay. Now a similar case, suppose a body, ring or a disc or a sphere, anything. It is initially it is spinning, means it is rotating only. It is in pure rotation. And that purely rotating body is kept over a rough horizontal surface. So initially it will be in pure rotation. The frictional force acting on it discourages rotation and encourages translation. So the friction provides angular retardation which will reduce omega, and friction provides linear acceleration which will increase linear velocity. So omega goes on decreasing and linear velocity V will go on increasing. Again at a certain stage V will become equal to omega r, the body starts pure rolling. If a spinning body is kept on a rough horizontal surface, see the body will again start rolling before it comes to rest or before it falls or overturns. Okay. And see what would be the angular velocity when it starts pure rolling. That is omega equal to omega 0 divided by 1 plus r square divided by k square. Okay. Children, I have explained everything from basics to advanced. Okay, everything. So you need not expect anything beyond this. Everything I have explained. See, if you take any question from rotational motion, see, to solve that question you will get the necessary tool from this video. Simply take that tool, apply and find out the answer. Okay, thank you for watching this video.